This is Radhika. I am going to give a video lecture on electrical engineering and electronic devices, subject code 18E 205C. So, in last class, we discussed a few topics about electrostatics. Today, we are going to discuss about electrostatic fields, plotting of electrostatic fields, comparison of electrostatic and magnetic fields. So, in last class, we discussed introduction of electrostatics and permeabilities of absolute permeability, relative absolute permittivity, relative permittivity, and, and we solved simple problems. So, actually, what is permittivity? Permittivity is the property of a medium that affects the magnitude of force between two charges. Every charge placed in a medium liberates electrostatic flux through the medium. This flux affects the magnitude of force between charges. Some media focus this flux more strongly. This property of medium to focus electrostatic flux, which affects the magnitude of force between two charges, is called permittivity. The greater the permittivity of a medium, the lesser the force between charged bodies placed in it. Each medium has two permittivities. They are absolute permittivity and relative permittivity. Absolute permittivity is actual permittivity of the medium. It is denoted by the Greek letter epsilon and is measured in farad per meter. The absolute permittivity of air or vacuum is denoted by epsilon naught and is equal to 8.854 into 10 to the power minus 12 farad per meter. The absolute permittivity of any other medium is more than absolute permittivity if relative permittivity as compared to vacuum is epsilon r. Then absolute permittivity of a medium epsilon is equal to epsilon naught epsilon r. Relative permittivity. It is defined as the ratio of permittivity of any medium to the absolute permittivity epsilon naught of air or vacuum. It is denoted by the symbol epsilon r. It and has no units. Relative permittivity epsilon r is equal to epsilon by epsilon naught. The relative permittivity of a medium is measured with respect to the permittivity of vacuum or air. It has got different values for different mediums. The relative permittivity of vacuum or air with respect to itself is 1. That is, epsilon r is equal to 1. Its value is 223 for paper, 3 to 7 for mica, 5 to 10 for glass, 80 to 82 for paper, etc. So today today we are going to discuss about electric field, electric lines of force, properties of electric lines of force, and plot the electrostatic field due to isolated positive charge, isolated negative charge, unlike charges side by side, like charges side by side. Electrostatic field. According to Coulomb's law, when a charged body is placed near another charge, experiences a force of attraction or repulsion depending upon the kind of charge. The region or space in which a charged body experiences a force of attraction or repulsion is called an electric field. According to Coulomb's law, when a charged body is placed near another charge, it experiences a force of attraction or repulsion depending upon the kind of charge. The region or space in which a charged body experiences a force of attraction or repulsion is called an electric field. Theoretically, the electric field due to a charge extends up to an infinite distance, but practically it exists up to a certain distance. As the distance from the charged body increases, the effect of electric field decreases, and hence its effect practically dies away very quickly. Theoretically, the electric field due to the charge extends up to an infinite distance, but practically it exists up to a certain distance. As the distance from charged body increases, the effect of electric field decreases, and hence its effect practically dies away very quickly. The space around a charged body is always under stress and experiences a force on another charge when placed near to it. Space around the charge in which another charge experiences a force is called electrostatic field, where Q is the charge. Observe the diagram. In this diagram, Q is the charge and R is the radius of the field. Next, electric lines of force. The electric field around a charged body is represented by imaginary lines are called electric lines of force. They are called electric lines of force because forces are experienced by charges in the region. The direction of force at any point is given by the tangent to the line of a force at the point. The lines of force always originate or emanates from positive charge and end converge on the negative charge. The electric lines of force have or enter the charged surface normally, that is tangentially at 90 degrees. As per SI system of units, one line of force emanates from a unit charge. The electric field around a charged body is represented by imaginary lines called electric lines of force. They are called electric lines of force because forces are experienced by charges in this region. The direction of force at any point is given by the tangent to the line of force at that point. The lines of force always originates or emanates from the positive charge and end or converge on the negative charge. The electric lines of force leave or enter the charged surface normally or tangentially at 90 degrees. As per SI system of units, one line of force emanates from a unit charge. So here in this diagram, they emanate from positively charged body. So here this diagram is the positive charged body, and the force of lines will be emanate from the positively charged body, and they end at a negative charged body. The electric field around a charged body is represented by lines of force. The lines of force always emanates from positive charge and ends on the negative charge. It shows the electric field due to an isolated positive charge in which the lines of force directed away from the charged body. The electric field due to isolated negative charge in which the lines of force directed towards the charged body. The lines of force for the two equal and opposite charges and for two equal and similar charges separated by a distance can be drawn in figure. It shows the electric field between unlike charges, positive charge and a negative charge. It shows the electric field between like charges, between two positive charges and between two negative charges. The electric field around a charged body is represented by the lines of force. The lines of force always emanates from positive charge and ends on the negative charge. The electric field due to an isolated positive charge in which the lines of force directed away from the charged body. So these two are the isolated positive charge and isolated negative charge. So here is the positive and negative charge. These will be attracted. The electric field due to isolated negative charge in which the lines of force directed towards the charged body. The lines of force for the two equal and and equal and opposite charges and for two equal and similar charges separated by a distance can be drawn. The electric field between unlike charges are positive charge and negative charge, whereas it shows the electric field between unlike charges between two positive charges and between two negative charges. Properties of electric lines of force. They are imaginary lines of force. They start from positively charged body. They ends at negatively charged body. They never intersect each other. They are elastic in nature. So here the lines of force will be enters for positive and emanates in negative charge. They are always normal to the surface. The lines of force in the same direction always repel each other. The lines of force in the opposite direction always attracts each other. Here, this image is for isolated positive charge. Isolated positive charge. An isolated positive charge is shown in this figure. The electric lines of force is seen to be radiating out from the surface of the positive charge. The lines of force are normal to the surface. This is the isolated negative charge. Isolated negative charge. In isolated negative charge is shown in figure. The electric lines of force is seen to be entering into the surface of the negative charge. The lines of force are normal to the surface. Like charges side by side. So, force of repulsion. In case of there is any two positive charges, there is a repulsion, and same also there is a negative same charges, that will also force of repulsion. So, like charges side by side. In the figure, two like charges are placed side by side. Two positive charges or two negative charges are placed side by side. There is a strong force of repulsion between the two like charges. So, unlike charges side by side, force of attraction. There is a two unlike charges, positive charge and negative charge. Here the force is attraction. The force is attraction. Unlike charges side by side. In figure, two unlike charges are placed by side. One positive charge and one negative charge is placed side by side. There is a force, there is a force of attraction between the unlike charges. Next, we go for few definitions. First, we go for electric flux pipe. The total number of lines of force emanating from positive charge is called electric flux. Electric flux is denoted by Greek letter pi and is measured in coulombs. In coulombs. Electric flux pi for a charge of q coulomb is equal to q coulombs. Electric flux psi is equal to q coulombs. The total number of lines of force emanating from a positive charge is called electric flux. Electric flux is denoted by Greek letter psi and is measured in coulombs. Electric flux psi for a charge of q coulombs is equal to Q coulombs. Electric flux psi is equal to Q coulombs. The electric field is represented by electric flux in the same way as a magnetic field is represented by magnetic flux. However, electric flux paths are not closed loops like magnetic flux paths. The electric field is represented by electric flux in the same way as a magnetic field is represented by magnetic flux. However, electric flux paths are not closed loops like magnetic flux paths. The total number of electric lines of force is called an electric flux. Unit is Coulomb. Next, electric flux density. So, electric flux density is the total number of lines of force in an electric field per unit area is known as electric flux density. It is denoted by letter D, is measured in coulombs per meter square. The total number of lines of force in an electric field per unit area is known as electric flux density. It is denoted by the letter D and is measured in coulombs per meter square. Electric flux density D is equal to electric flux psi by area, that is coulomb per meter square, that is equal to Q by A coulomb per meter square. Electric flux density D is equal to electric flux psi by area. Units is coulomb per meter square. The electric flux passing per unit area and normal to the surface is called electric flux density. Symbol is D, that is equal to psi by area. Unit is coulomb per meter square. Next, tubes of electric force. Faraday tube, surface of charged body. Faraday explained about the Faraday's loop. Tube of electric force. Using of this one, the force will be how the force will be applied on positive and negative charge. Faraday tube. According to Faraday, lines, lines emitting from a charge are infinite. Lines emitting from a charge are infinite. From each point of small area will emerge lines of force as shown in figure. From each point of small area will emerge lines of force as shown in figure. The shape of the total number of lines of force from the small area will be a tube called tube force. The shape of the total number of lines of force from the small area will be a tube called as tube force. The total number of such tubes of force radiating is charge Q. The total number of such tubes of force radiating is charge, that is Q. So this is the electrostatic lines of force. From positive charge it will be emanating the charge. This is the magnetic lines of force. Magnetic lines of force. Here is the Comparison between electric lines of force and magnetic lines of force. Here there is a important points of electrical lines of force and magnetic lines of force. Here we have almost 11 differences between electrostatic lines of force and magnetic lines of force. First one is a charged body establishes electrostatic lines of force or electric field. A charged body establishes electrostatic lines of force or electric field. In magnetic lines of force, a magnet establishes magnetic lines of force or magnetic field. A magnet establishes magnetic lines of force or magnetic field. In electrostatic lines of force, the total number of lines of force in an electric field is called electric flux. In magnetic lines of force, total number of lines of force in a magnetic field is called magnetic field. In electrostatic lines of force, electric flux psi is measured in coulombs, symbol C. In magnetic lines of force, magnetic flux pi is measured in Weber's WB. In in electrostatic lines of force, the electric flux density D is equal to pi by psi by A, that is equal to Q by A coulomb per meter square. In magnetic lines of force, magnetic flux density B is equal to Q by A Weber per meter square. In electrostatic lines of force, the property of medium in electrostatic field is called permittivity epsilon. In magnetic lines of force, the property of medium in magnetic field is called permeability mu. In electrostatic lines of force, absolute permittivity epsilon naught is equal to 8.854 into 10 to the power of minus 12 farad per meter. In magnetic lines of force, absolute permeability 4 pi into 10 to the power of minus 7 Henry per meter. In electrostatic lines of force, an isolated positive or negative charge exists. In magnetic lines of force, an isolated north or south pole does not exist. Electric lines of force emanate from positive charge and ends on negative charge. In magnetic lines of force emanates from north pole and ends on south pole. In electrostatic lines of force, the direction of lines of force at any point is always normal to the surface of the body. In magnetic lines of force, the direction of lines of force at a point is not normal to the surface of the body. In electrostatic lines of force, these lines of force do not pass through conducting substances. In magnetic lines of force, these lines of force pass through conducting substances. So last point, in electrostatic lines of force, they do not form closed path. In magnetic lines of force, they form a closed path. So here, here a positive or negative charge establishes electrostatic lines of force. In magnetic lines, a current carrying conductor establishes magnetic lines of force. In electric lines of force, develops electric flux. In magnetic lines of force, develops magnetic flux. In electric lines of force, electric flux density D is equal to psi by A, means Coulomb per meter square. In magnetic lines of force, magnetic flux density B is equal to pi by area, Weber per meter square. In electric lines of force, permittivity epsilon is equal to epsilon naught epsilon r. Here epsilon naught is equal to 8.854 into 10 to the power of minus 12 farad per meter. In magnetic lines of force, permeability mu is equal to mu naught mu r. Here mu naught is equal to 4.2 to the power minus 7 Henry per meter. In electric lines of force, these lines do not form closed path. In magnetic lines, these lines form closed paths. They are normal to the surface. They are not normal to the surface. In electric lines of force, these lines do not pass through conducting substances. Magnetic lines of force, these lines pass through conducting substances. In electric lines of force, isolated positive or negative charges exist. In magnetic lines of force, isolated north or south poles does not exist. Comparison between electric lines of force and magnetic lines of force. Both electric and magnetic lines of force behave like electric rubber bands. Both are imaginary lines of the force. Next, electric field intensity. Electric field intensity, the force experienced by a unit charge placed the force experienced by a unit charge placed at a point is known as field strength H or E. Electric field intensity at any point within an electric field may be defined in either of the following three ways. First one is electric field intensity or field strength at a point in an electric field is defined as the force experienced by a unit positive charge placed at that point. It is denoted by letter E and is measured in Newton per Coulomb. If the charge of q coulombs placed at a given point within an electric field, it experiences a force of F. Then electric field intensity E at that point is given by electric field intensity at a point is E is equal to force experienced F by charge q, that is equal to Newton per Coulomb. Let a unit positive charge plus 1 Coulomb is placed at a point P at a distance of d meter from charge q coulombs. Then, by definition, the electric field intensity at point P is the force acting on plus 1 coulombs placed at that point. Electric field intensity, that is equal to force on positive 1 coulomb, that is equal to q by 4 pi epsilon r d square Newton per coulomb, that is equal to 9 into 10 to the power of 9 into q by epsilon r d square Newton per coulomb. Electric field intensity may also be defined as equal to the lines of force passing normally through a unit cross section at the point. Suppose there is a charge of q coulombs, the number of lines of force produced in it is q by epsilon. q by epsilon. Electric field intensity at any point in an electric field is equal to the potential gradient at the point. Electric field intensity at point E is equal to minus dV by dx, that is volts per meter. The force experienced by a unit charge placed at a point is known as the field strength, that is E. It will be measured in Newton per coulomb. So, this is the electric field intensity. Here Q1 and Q2 are the two charges, may be positive or negative. Here it is the permittivity, relative permittivity, and the distance between Q1 and Q2 is d. It is some medium. So, Q1, Q2 are the charges, d is the distance between them, epsilon r is the relative permittivity of the medium, E is the electric field strength or electric intensity, electric field intensity. Electric field intensity. Q1 is equal to q coulombs, Q2 is equal to 1 coulomb. The force experienced by unit charge at a distance of d meters is E. E is equal to F is equal to q by 4 pi epsilon d square Newton per coulomb. Another definition: electric field strength is the lines of force passing normal through a unit area at the point. Q is equal to charge of a body, Q by E is Q by epsilon is equal to lines of force produced by the charged body. A is equal to area through which lines of force passing in meter square. Next is the E is equal to q by epsilon by A, that is equal to q by epsilon into A, that is equal to q by A by E. So, finally, that is E is equal to d by E, Newton per coulomb or volt per meter, where d is equal to q by A. Definition 3. Electric field intensity at any point is an electric field is the potential gradient at that point. Electric field intensity at any point in an electric field is the potential gradient at that point. V r dV, potential difference between 2 points. Dr dx, distance between 2 points in meters. Capital E is equal to V by small d or dV by dx volts per meter, and E is equal to dV by dx volt per meter. Here, next we go for Gauss theorem. Next we go for Gauss theorem. Here, Gauss theorem is the this theorem was proposed by German mathematician Carl Friedrich Gauss. This is one of the most useful theorem in the area of electric fields. The total electric flux psi emanating from a closed surface is equal to the total charge enclosed by the surface. The total electric flux through any imaginary closed surface is equal to the total quantity of all charges enclosed in the surface. So this is the diagram for uh, Gauss Gauss theorem. So here in this medium, it has the Q1 minus Q2, Q3, Q4 are the charges, imaginary surface and charges, positively and negatively charged Q1 minus Q2, Q3 and Q4. Here total electric flux psi is equal to sigma I is equal to 1 to n Qi. If there are number of charges of Q1, Q2, Q3 and Q4, then according to Gauss theorem, the total flux crossing the surface is given by psi is equal to Q1 minus Q2 plus Q3 plus Q4 coulombs. So that is sigma I is equal to 1 to n Qi. Next we go for electric potential. The electric potential at a point in an electric field is defined as the work done in bringing a unit positive charge plus 1c from infinitely to that point. It is denoted by the letter V and is measured in volts. Electrical potential V is equal to work done by charge, that is equal to W by Q volts. An electric charge causes an electric field around it, which theoretically extends up to infinity. If any charge is placed in this electric field, it will be attracted or repelled depending on the nature of the charge. When it is moved, the work will be done against or by the force acting on the charge due to electric field. Consider an consider an isolated charge plus q coulomb is placed in the space. If a unit positive charge plus 1 c means coulomb is placed at infinitely, the force on it is 0, because F is equal to 9 into 10 to the power 9 q into 1 into 1 by d square, as d is directly infinity, F is equal to 0. If the unit positive charge is moved towards plus q, a force of repulsion acts on it, because like charges repels each other, hence work is required to be done to bring it to a point like A. When the unit positive charge is at point A, at some point it has some amount of electrical potential energy which we commonly call electric potential. The closer the point to the charge, the higher will be the electric potential at that point. Therefore, electrical potential at point due to a charge depends upon the position of the point. The potential is zero if the point is situated at infinity and is maximum if it is situated near to it. It is clear that if the field is due to a positive charge plus q, there is a force of repulsion between plus q and unit positive charge, and hence work will be done against the electric field. However, if the field is due to the negative charge, there is a force of attraction between minus q and unit positive charge, and hence work will be done by the electric field. In practice, the potential energy or potential of the mass depends upon the position of the mass with respect to Earth. Hence, Earth is chosen as zero potential. It is because Earth is such a huge conductor that its potential practically remains constant. Hence, a body whose potential is higher than that of the Earth is said to be a positive potential, and one whose potential is lower than that of the Earth is said to have a negative potential. Hence, if a positively charged body is connected to Earth, charge will be flow from body of the Earth because the body is has higher potential than the Earth. The charge continue to flow from positively charged body to Earth until the potential of the Earth also becomes the same as that of the body. Suppose if a negatively charged body is connected to Earth, charge will flow from the Earth to the body because the Earth has higher potential than the body. The charge continues to flow from Earth to negatively charged body until the potential of the body also becomes the same as that of the Earth. So, this is the electrical potential. So, here if UPC is moved towards Q through a small distance of dx meters, then work done is equal to force into distance, that is equal to q by 4 pi epsilon naught x square into minus dx. So that is equal to after integration, it is integration of q to q by 4 pi epsilon naught x square dx, that is equal to minus q by 4 pi epsilon naught into minus 1 by x up to infinity to d. After calculation of that one, we will get q by 4 pi epsilon naught d. This work is numerically equal to potential at that point in volts. V is equal to q by 4 pi epsilon naught d, that is equal to 9 into 10 to the power of 9 q by d in air. 9 into 10 to the power of 9 q by epsilon r into d in any other medium. This is the potential difference. 1q and 2 UPC, VA and VB, and distance between from Q D1 and D2. The potential difference between it may defined as work done in moving a charge of 1 coulomb from one point to another point. Consider 2 points A and B as shown in figure. Let VA and VB are the potentials of two charges A and B. VA is equal to Q by 4 pi epsilon naught D1 volts. VB is equal to Q by 4 pi epsilon naught D2 volts. The potential difference between A and B is VAB. VAB is equal to VA minus VB, that is equal to Q by 4 pi epsilon naught D1 minus Q by 4 pi epsilon naught D2, that is equal to Q by 4 pi epsilon naught epsilon r into 1 by D1 minus 1 by D2 volt. So we have the few quiz questions. Electric potential in air is 9 into 10 to the power 9 Q by D volts. Electric field strength is measured in coulomb. So electric field strength measured in Newton per coulomb. So these are the few quiz questions. So this is the today topic, field patterns and frequently asked questions. Write any four properties of electrostatic lines of force. Compare electrostatic and magnetic lines of force. Define electric field. Write any four properties of electric lines of force. Plot field patterns of the following: isolated positive charge, isolated negative charge, and positive and negative charges side by side. So this is the today's topics. In next class we will discuss about other topic. Thank you.